Welcome to the Rare Earth Exchanges podcast, where power, politics, and the world's most coveted materials collide. Rare earth elements power the backbone of tomorrow's most critical technologies. With China dominating global production, the U.S. and its allies must align strategically to ensure a stable future. This urgency prompted tech entrepreneurs Daniel O'Connor and Dustin Olson to launch Rare Earth Exchanges, a news and insight platform built to equip stakeholders and decision makers with the tools and intelligence needed to reduce dependency and build prosperous resilience. Let's get into it.
Hey everyone, welcome back to the Rare Earth Exchanges podcast. I am Dustin, your host, joined by my co-host Daniel, and we have a return guest, Travis McLing, who is a geologist at the INL, the Idaho National Laboratory. Travis, welcome back to the show. How are you?
I am great, and it's good to be back. Thank you.
Yes, Travis, we were so enthralled with the conversation we were having with you before that we just felt like sharing the stage with somebody else was not enough time. So we want to dive deeper into some of your knowledge, get more of your perspective about the rare earth industry and even just some of the basics from a geologist's perspective. One of the things, just to kind of level set here for those who are discovering this space and trying to understand a little bit better, can we talk about or better understand why rare earths aren't actually rare, but maybe getting them out of the ground is a little harder, and that makes it rare?
Yeah, I think that's a really good question. I wish more people would ask and oftentimes I'll answer questions to people trying to lead into a question like this, is that we are victims of geology. And when it comes to that, and processes that concentrate base metals are far more common than they are that concentrate rare earths. Let me tell you what I mean by that. So the source material for rare earth elements are largely carbonatite magmas, and these are they're amazing features of our Earth system, but they're incredibly rare. They make up about 0.1% of all magmatic features on the surface of the Earth. In fact, on the Earth today, there's only one active carbonatite volcano, and that's in Tanzania in the East African Rift. So you really need these hydrothermal magmatic processes to concentrate copper and gold and silver and zinc and other processes. Rare earths are completely different when it comes to that. So the first thing you have to do is we have all the heat in the mantle, and we could go into great detail about talking about mantle structures and whatnot, but it's the part of the Earth that sits below the crust. It's the dynamic heat flow, driving force for plate tectonics, for magma processes. In order for you to have a carbonatite magma that is enriched in rare earths, first you have to have a special geochemical process happening in the magma. So the magma has to kick off a process that is pretty rare, and that is where you actually enrich the magma. So the very source of the melt has to get enriched through a process that includes, it's called fractional crystallization, and that magma also had to have been injected with other materials to enrich it. So we're already talking about 3 generations or 3 steps away from really common type Hawaii type volcanoes, which mantle produces on a regular basis. So then you take that magma, that part of the mantle that's been enriched, and you've now fractionalized. That means you've separated crystals from it, and you separate that in a very special way so that you end up with a very special type of CO2 enriched magma. Now you have that part of the mantle deeper in the mantle. It's sitting down in there looking for a way to get to the surface. Well, it doesn't come to the surface in the typical volcano kind of way. You have to basically have like rift zones, like the East African Rift, where the Earth is being pulled apart at a rate that's high enough to allow that piece of the magma to shoot to the surface. And I've really simplified the process. This is what volcanologists study a whole PhD career on trying to understand and explain. But you get that magma to the surface, and then you have to rely on different processes to allow for enrichment and allow in the Earth's crust and allow for subsequent erosion to get you to that magma after it's been in place. So I know I've probably confused everybody, but
Well,
it's
I have a
percent.
this is very important. This foundational geology is very important. I have questions. Now, this magma that essentially gets processed by Mother Nature and the crystals are separated, and then it comes up through some, dikes or some kind of rifts. Is that when it comes up, is that a igneous or is that a volcanic?
Igneous gets it there. Volcanic is the surface. So some of these make it to the surface and erupt.
Mm-hmm.
Some of them get trapped within the crust and get stuck there. So they're both. Volcanic are where we actually get to go take pictures and see a volcano erupting. And then igneous processes are the processes that involve the movement of magma.
Right.
So volcanic is igneous, but igneous isn't necessarily always volcanic.
Right. And so, like, if you took Mountain Pass as an example, would that geology, it'd be nice to apply it, if you're good with this, Dustin, to take the concept that Travis just explained to us and maybe just categorize a couple famous sites. So if you take Mountain Pass, is that exactly what happened? What brought that material up, and what is that material?
Yeah, that's correct. And so these are really interesting magmas. In fact, when I was a kid or a young guy going to graduate school and undergraduate school, I studied these things and learned about it. I thought I would never touch one in my life. I thought they only existed in one place. Well, it turns out there's a whole number of places on Earth where carbonatites exist. Some of them are in my neighborhood, just up the road. Some of the bigger ones are at Mountain Pass, Ionobo, Olympic Dam in Australia. So there are places where we call these supergiants like Ionobo and Mountain Pass exist, and that's exactly the process we talked about. Is that the mantle is able to release a very specialized, a very enriched type of magma, and essentially these magmas are limestone that's being extruded onto the surface of the Earth. So it's a very unusual. They're low temperature, and they have really incredibly unusual mineralogies that are associated with them. I have a piece of one right here. For most people walking up on an exposure, say in our salmon area, you would think that you're walking up on a limestone deposit. So they have a wide range of compositions, but yeah, that's essentially what happens. And in a few places like Mountain Pass and Ionobo, very large systems develop. Other places that are associated with heavy rare earths tend to be smaller, more dike-like deposits rather than these massive supergiants. I hope that helped, Dan.
Yeah, that's very helpful. Go ahead. I have more questions, but Dustin, please keep going.
Yeah, so just kind of a follow-up question to this process, how the rares are kind of found and created. Why are some areas, deposits, more economically viable than others? Like, why is that an issue that we are concerned about?
Yeah, I think that's another really good question. And it's, again, we're subject to geologic processes. The larger deposit and the more rock you can move, the more economic these systems tend to be. Also, you have to have concentrations of rare earths, for example, that are high enough to warrant being mined. So in a lot of these cases, you have percentages. If you're mining a copper deposit, a lot of these copper deposits are a few tenths of a percent copper. Or if you go into a rare earth deposit, you're talking total rare earths that are from say 1 to 5% total rare earth. So you have to have grade is everything. Everything else set aside, grade is everything, because it directly ties to the cost of moving material and how much money you can make by recovering it. So that's why the deposit type matters. And the other part that matters is that what else is in that magma? What else is in that ore body? So, for example, some of these deposits like Ionobo and Mountain Pass have quite a lot of thorium in them. And thorium becomes problematic because it costs you more to operate. It costs you more to secure the tailings pile. It costs you more in a lot of different aspects to handle that radioactive component. Other deposits, which are secondary deposits like ionic clays, which are the result of weathered magmatic bodies, weathered ore bodies. These are a lot less because they're less encumbered with thorium, and the rare earth elements are bound more loosely. That means they're stuck to clays as opposed to being locked within crystals like bastnasite and xenotime. There's a lot of different components in this question, and this is where I get to when people say, "Oh, well, we have rare earth, let's go mine them." Well, there are a lot of complexities. If you want to target heavy rare earths, there's a very specific type of mineralogy one wants to look at, and those deposits tend to be much smaller and are very different than the light rare earth enriched deposits like Ionobo and Mountain Pass. And that matters, which I'm sure you'll ask in a minute why heavies versus lights matter.
Yeah, I mean, the heavy, based on everything that we have learned, Travis, and that we now analyze as we learn more, is there's less of a, and tell us if we're wrong here, there's less of a bottleneck and crisis with lights rare earths than there are heavy rare earths. And what'd be fascinating to understand I make this assumption that ionic clays, other clays in tropical areas are where heavy rare earths are. Of course, it's more than that, but if you could educate us about how you find heavies, how they're different, and why they're more rare.
Well, let's start now. Daniel, I'll answer your question backwards with the end first, and then hopefully I'll get to the start. So when one looks at a deposit like Mountain Pass or Bayan-Obo, which are the famous ones, they're about 1%. So you'll hear often rare earth deposit. Okay, what does that mean? That doesn't mean anything to me in terms of how we want to address the occurrence and how we want to mine it. What I want to know is whether it's heavy or light enriched and what the concentration of each is. So in a typical big deposit like Mountain Pass, you have about a 1% of the rare earths that are in that deposit are heavies, and about 99% are lights. And if you look at just the total cost, you see that there's can be an orders of magnitude difference in the cost between cerium and some of the heavies. So that does matter. Is that when you look at these things, is that you'll often hear a world-class discovery of rare earths, and they'll pronounce it as a total rare earth oxide. Well, that's nice, but really what matters is we don't need as many lights, and there's way more of them, and we need a lot more heavies, and there's way fewer of those. In fact, it's about 100 times more abundant for the light end of the rare earths than it is for the heavy end.
And why, Dustin, if I may, why geologically? Why is that geologically?
Yeah, and it has to do with just abundance, the way the universe is put together. It also has to do with how light rare earths, even though we all hear that they're very similar to each other, that between lanthanum and the 15 elements in the rare earth category, and then you have 17 if you count yttrium and scandium, they're like nearest neighbors. They behave a lot alike. Well, they behave a lot alike, but not exactly alike. On the light end, so we have a thing called lanthanide contraction. So lanthanum has an ionic radius that's much bigger than lutetium. As a result, fit more easily, the lights fit more easily into minerals than do the heavies. And when the heavies go into specific minerals, like xenotime, for instance, it's way harder to process xenotime than it is to process bastnasite, which is a light rare earth element accumulator. And I know I'm speaking a lot of jargony stuff, but the fact is you have more lights in the earth, and they more readily form minerals. The heavies occur less frequently, and they form more, in a general sense, they generally form more stable minerals that are much harder to crack and release the rare earths. So xenotime's a great mineral. It's full of rare earths, especially heavies, but it's much harder to crack than bastnasite. It's a carbonate versus a phosphate. And therefore, and because of that contraction and how they fit into the crystals and their abundance, and of course, and we have this really interesting thing about the f orbitals in the electron configuration. And I'm not going to go into that because that's a whole physics discussion. All of these things all contribute to the end statement, which is naturally lights are more abundant than heavies.
More abundant. So just to finish this topic on the ionic clays, why is it that was Myanmar, parts of Vietnam, southern China, parts of Brazil, that the concept of ionic clay and heavies seem to go hand in hand? Is there anything to that?
It is, and it has to do with the sources. So remember, the clay in and of itself is not where the rare earths began. They began in a granite or something else that was more enriched in heavies versus a carbonatite, right? So if we weather a carbonatite, we end up with the clays associated with that being enriched in lights. But here we have a different source. So when I look at an ionic clay in my hand, I know, well, this isn't where it originally started. It started as a different rock, and geologic processes liberated it, and then clays are really sticky from a geochemistry point of view. They like to grab onto cations, and so they grab onto them. And they grab onto them in the ratio that they were released from the original ore body. That's why, and clays, because their process of weathering, that's why the tropical environments they're way more common, because clay form more readily in those kinds of environments. That clays represent a stable end member for silicate, right? They're not, when you have a magma that is erupted and forms a granite body, it's not really happy being granite. It wants to be in its lowest energy state, so it weathers, and then it ends up in a low energy state, which is a clay. and they're quite happy and can be there. So that's why they end up moving from one to the other type of rock. And please tell me if I've confused you in the answering process, but it's all
No,
principle.
this is great. And think about it. The members, there's investors, there's prospectors. So there must be a methodology to prospect for heavy rare earths, right? I mean, there must be mapping technology, AI that are being used to find locations that may have better prospects.
Yes. And we know where lots of these deposits are globally within our own country, and we know where a lot of them are. And that's not the problem. The problem is that economics still drive the day. And so when we talk about critical minerals and we talk about rare earth elements and we talk about how important they really are important. But we sell them by the kilogram. You sell gold by the ounce. You sell rare earths by the kilogram. For instance, dysprosium or terbium. Let's go with terbium. Terbium typically has about a $1,200 per kilogram price, right? That's more like what copper. It's more than copper, but it's sold at the same kind of mass. Copper's sold by the pound, and here where the Shanghai market goes by the kilogram. But anytime you have a material that's really important to you, but its value is in a block this big instead of a teeny, it's way easier to make money going after gold than it is going after, say, terbium.
Yeah.
Secondly, is that these deposits, except for the ionic clays, there are non-ionic clay heavy enriched systems in the U.S. and they tend to be a lot smaller. So when you go do exploration, so I'll take my XRF and I'll look at rocks and we'll do an analysis and we'll look at the deposit and we'll say, well, it's heavy enriched, it's light enriched. They almost all have more heavies than lights, but enriched means that that slope is tipped more in favor of the enriched in heavies. That's really not the hard part. The hard part is how are you going to mine a vein that's as wide as my desk or as my office, as opposed to, these big deposits. One thing you should understand is these big deposits are really iron mines, so they are massive, and then they're associated with iron oxide, lots and lots of it. And just so happens that now in the last 30 years we've developed a market for rare earths, so now they're iron deposits with rare earths associated with them. But still, it comes back down to that whole process is that the global marketplace. So if you look, let's just take the total heavies that are sold around the globe is about 19,500 metric tons in 2023. So that's the total amount of the heavies. That's the elements, thorium, dysprosium, and yttrium and scandium are included in there. Okay, copper. We produce 23 million metric tons of copper in a year. So just do that. It doesn't take a lot of first arrivers to swamp a market where you only produce 19,500 metric tons in a year. So if you bring two big mines on, you have a suppression of the market just naturally. Forget what China's doing. Just the marketplace becomes saturated pretty quickly because compare it to zinc, compare it to copper, compare it to any other base metal out there, and you find that they're critical but not terribly valuable, if that makes sense to you.
Yeah, that does. On that paradox, on the one hand, you have this, especially with the heavies, extreme importance in all sorts of high-tech magnets and assemblies that are important for very, very valuable output, fighter jets, what have you. The market price isn't that high when all things being equal. So you have this real quandary, right? And then you have the Chinese situation where they've sort of used a hybrid economy to kind of control that geology and the chemistry. It's a real dilemma. I mean, we don't have to go too deep into that topic, but that is part of the fundamental problem, isn't it?
It is part of the fundamental problem. And that's why if you take a look at and I'll take a little sidetrack here that's really not as much technical as it is federal government involvement. You take like the Audrey Robertson's organization at Department of Energy, which owns the critical mineral space, and you take Bert Thomas's division, which is critical minerals, and look at where they're investing and how they're partnering. They are trying to tackle this market imbalance where we can produce all the lights we want, and we practically have to give them away. But the heavies are much harder to produce, and they're much more difficult to obtain. I mean, in an electric motor, the imbalance is roughly 95-5. You use about 95 parts of neodymium to about 1 5 parts of dysprosium. If that was flipped, then you would see market forces driving heavies into that. So as scientists and as the funding agency through opportunities like Metallic and others that the federal government is funding, we can start addressing some of those shortfalls. Because really, to get to that more valuable product, you have to produce so much cerium. What do you do with it? The market becomes saturated quickly. Are you going to store it on site, or what do you do with it? Because it comes as a consequence. And not only that, but then you have to think about the complexity of the separation process. You have hundreds, if not 1,000, separation stages to get the heavies cleaned up and ready to go to market. So it costs a lot more. But the market differential isn't huge, right? It's not like it's 10,000 times more expensive.
That's right. And the markets, you would think that the market would pull up that price because it's so hard to get, but it doesn't. It stays. Part of it might be the Chinese influence, but so it's really, really fascinating. I don't think today, Dustin, we're going to get into separation. That's a really separate topic, keeping with the geology. If we look at, Dustin, do you want to chime in on a couple questions, then I can circle back?
Yeah. So, Travis, listening to you talk about lights and heavies seem to be not only harder, but also more popular in terms of demand. Can you provide just a quick summary of why they're different and maybe why heavies are highly sought after?
Yeah. So I'll stay away from answering it like Sheldon Cooper would, this is really a physics answer, and I'll stick to the geologic side of things, and answer it at a pretty high level. Dysprosium, for instance, there is no substitute for it because it works in high temperature magnets. So high temperature applications such as aerospace, missiles, these kind of things, you've got to have that there. It doesn't make up the whole magnet, but its presence in the magnet makes the magnet more resilient to temperature swings. And right now, we don't have any substitute for that, right? There are other ways to make magnets, but if you want a high temperature magnet, you really have got to stir in the dysprosium. Terbium, for instance, you use it in phosphors and magnets, and there's limited alternatives to that as well. Unlike the light rare earths, where there's sometimes more opportunities for substitutions with cheaper metals, when it comes to the high temperature, these really high field strength areas, you don't have any choice. You've got to go to them, and that's why they're so important. But again, you don't make the magnet completely out of dysprosium. It's a neodymium magnet you dope with dysprosium. And like I said, if it would switch, right? If it was a dysprosium magnet you doped with neodymium, suddenly the market would change. It would flip, and deposits like Bayan-Obo and the Chinese forcing factors from Bayan-Obo wouldn't be nearly as beneficial to them, because now the market would have to go out and exploit these other resources. I don't know if that answered your question. I've been trying to stay away from like I said, talking about the F orbital issue and why that matters in these things. But in the end, they have a very specific need, and there isn't a way to get away from using them if we're going to fly F-22s and F-35s, and we're going to put hypersonic missiles into space. It just got to have them.
Yeah, no, I think you did a great job answering the question. And the examples of the applications like F-22s, things like that, those are high stakes, right? Like if it fails, it's just catastrophic. And so
yes, sir,
we have to have kind of the only option, the best option. So that makes a lot of sense. And just as a tag along question to finding these deposits there and how they come, this is kind of maybe shifting gears a little bit, but what's the biggest upstream misconception that the industry might have? So investors or policymakers, what are we not understanding at the geology, the mining spot of the supply chain?
Yeah. Well, I'll often tell. So I get a lot of calls from industries that say, "Hey, we have this waste pile. We've measured it. There's rare earths in there. There's 250 parts per million rare earths," and they read somewhere that's a number that somehow meets market economics. But the reality is that it comes back to this whole story about we don't need as many rare earths as the world thinks we need right now, right? The total amount of rare earths compared to, say, copper or zinc or other metals that we produce on a regular basis, the mass needed isn't there. Now, we may get there at some point, but there's an assumption that if I have material, then there is a market for it. And it all goes back to that economic story. Can you produce it at the cost that can be resilient to Chinese market forces, that them suppressing a market long enough to keep you out of business, And number two is that can you get into business? So, we're looking at the United States, depends, their numbers vary, but you're looking at between, 17 to 20 years to get a known characterized deposit into business. So, but who's going to buy that material? That's part of our problem, is if we produce it right now in large quantities, we still have to ship it to Asia and have them ship it back to us as a refined or as a magnet or as a battery or whatever the case may be. We don't have the downstream production, the separations, the metallization, the manufacturing. Now we're trying to get there, but they have to arrive at the train station about the same time. You can't produce 10,000 metric tons of heavies and not have any place for them to go and be made into a final product. So that's what I wish. Now, miners understand this. And if you take a look at who owns the rare earth deposits in the United States and in the Western world, Canada, these are small. Some of them are small minus companies. They're not the Newmonts. They're not the Rio Tintos, right? They're not the Glencores. And the reason is that perhaps we talked about this before, is the market instability is way harder for them to de-risk. And the market's only been around for a couple decades. And so that creates a problem in this scenario. Is I wish people would just, what they would understand is that just because you have concentration doesn't mean it's viable. And if it is viable, doesn't necessarily mean you can beat your neighbor to the marketplace. Because while we need to produce more, we don't need 1,000 mines.
On that note, Travis, beautifully told to us. I mean, it makes total sense. We try to break apart and analyze all of these companies, upstream, midstream, downstream. We have these rankings, and we look at the ecosystems of the different upstream mine to magnet, and we try to understand where are they really at? Are they going to be able to separate and refine? Are they going to be able to have magnet producers? All of these things matter. So we totally get what you're saying. I mean, we're learning as we go. I had a question because, I heard you speak one time, of course, it's here in Salt Lake City, and it was fabulous. When did you first know we had a problem? If you go back in your career and just looking at the situation with terbium, dysprosium, and this imbalance, when did you first say to yourself, ooh, this looks like a problem?
Yeah. So if you know my story, I started out in the early 90s wanting to be a mining geologist. That's what I wanted to do. I was fascinated by ore deposits. But at that point, there just weren't jobs. The metal prices were down. The U.S. had moved out of the mining business largely, unless you were gold and silver. And even those mines were struggling. And so I took my trade to the Department of Energy and started cleaning up metal and mine sites. But in the early 2000s, there was an incident that happened between China and Japan. And in that, there was an argument, if I remember, it was over a fishing vessel, and the Chinese and the Japanese didn't see eye to eye. I think the Japanese ended up impounding the boat for some period of time, and China replied by cutting their rare earth element supply off. And this created a big problem. And that big problem was that suddenly the world wasn't quite ready for it, and there were a few around, but I saw, this is going to be a problem. If one country can control the distribution of a vital metal to the globe, we're in a serious problem. And so I began to dive in and to retool my career to begin looking at not just rare earths, although I did my PhD in part on rare earths, but the whole rest of the critical minerals. I didn't know at the time. I had no clue. I know we'd gotten rid of the Bureau of Mines in the 90s, and that was a big hit. But then I started looking around and realized that there's a whole suite of elements out there that we don't control our destiny. And rare earths are the first forcing function. So that's when I began to retool my career and to start begging and borrowing to build a little team that could start working on this. Now it took 10 years, but here we are, and the country's finally facing up. This is not right or left. It's not Democrat or Republican. Everybody recognizes that we have a problem, and that if this goes another 10 years, that this may be irrecoverable. You got to remember, the Chinese have been doing this for 3 decades. We've been doing this for 2 years in a really serious, we've had some investments by the federal government in the Critical Minerals Institute, other things, but really a focused effort for just maybe 3 to 5 years. What they're doing now is they've already got that, right? And so they're saying, hold my beer. And they're now doing what we're going to have to worry about in 20 years. They're already working on right now. They really have very little interest in selling raw metals to us, raw oxides. You know what they want to sell? They want to sell cars. They want to sell magnets. They want to sell supercomputer chips. That's what they want to sell because they make a whole lot more money doing that. And eventually you're starting to see it. The market tightens and they start moving into this high value product. You said China really being miners is what was their entree into the high tech world. And so that it's a long answer to a short to a short question, which was I saw this train wreck coming 15 years ago, nearly 15 years ago. I didn't know what to do about it at the time. So I picked myself up and I started to try to figure out ways to get myself entrenched in the small bit of effort that was going on.
No, it's a very important answer that you shared, and it makes total sense based on everything we're learning. This is a more profound question, and it's around there's this gap. There's the geological realities, then there's the separation chemistry realities. We advocate for subsidies, okay? We advocate for industrial policy. Like, we advocate, I believe INL should be at the center of everything, advising people. And we have to. So the question is, do we have to become sort of more like how they operate in China to cross this chasm, rebuild these supply chains? And this is a big question, Travis, but it's at a high level, it seems like it's too important not to. You can't just keep doing what you're doing. It feels like, you have to look at this challenge holistically, because it's not just about geology, chemistry, and magnets and business. It's about your national security. Any thoughts on that?
Yeah, of course I have. Of course I have a lot on that. It's kind of unsatisfying when as a geologist and geochemist, I look at these ore deposits and I look at them and how did nature put them together and how do we unstitch them and all the clever separation chemistries and things that we do. And then an investment banker hits me upside the head and says, listen, it's all about the economics. And that's kind of unsatisfying as a scientist because I figure that I'm clever enough that I can extract the minerals from here and everybody will want them. Reality is I can give a talk when I give a lot of talks. I can get up and give a talk and say it's about economics and then just go sit down. And that would really, that's really the end product. There's a lot of research that needs to be done to get there. And the economics of this whole story is what drive it. And I think we don't do policy here at INL. We inform policy and we do talk to policymakers at their request. But there has to be a way to stabilize the floor price. You cannot see billions of dollars in investment roll into this mining enterprise. Rare earths, gallium, germanium, doesn't matter. You can't see billions of dollars rolling into this if the end product is that China can kill your market for 5 to 7 years. Look what they're doing in cobalt. Jerva they were ready to open the mine and start producing concentrate, and cobalt went right through the floor because China flooded the market. Why do they flood the market? Because they can. China's mining a lot of copper in the Congo. You know what they get as a byproduct? It's a byproduct. They get cobalt. And so they have thousands of tons of cobalt that they can just throw into the market forever and ever. Now the Jerva mine is in care and maintenance.
Wow.
Because they've kept the price so low. So some way on a policy side, we have to figure out whether it's a national strategic stockpile that the consumers buy into, the businesses buy into, that allows the market price to be stabilized. I wished I was that clever in economics, but the answer has to be, it cannot be invest all your money and then lose it all because you can't survive in a market where China killed the price by 90%. And so that's part of this problem. Now, those of us working in the Department of Energy and working with the Department of Defense, we're working really hard to shave dollars off of the price to produce these elements. And we're doing a good job. And like I said, metallic is making huge inroads and has the potential to really be a market changer. But if we have to survive an order of magnitude decrease, the thermodynamics don't say that we can do that, right? We can't decrease the cost of production an order of magnitude below what the market currently is in order to defend against market manipulation. So what do? That's where Daniel, that's where the work that you and Dustin do really come into play here.
And on that, Dustin, I'll just have one more question for Travis. On that note, what we're observing and the chatter we hear, China has their own problems. They have an overproduction problem. They make too much stuff, and they're not very good at market mechanisms. They produce. Then all of a sudden, like, hey, we got a whole bunch of electric cars we got to get rid of. Now, they have cutthroat capitalism within their ecosystem, but then whoever wins, they kind of unleash them on the world, Now, there's chatter to get out of their own crises. They have to prime the pump of demand. So they're looking at further greenification, AI, digitization, the next level. That's going to require more of their heavy rare earths, especially. What if we get into let's just do a what if. What if all of a sudden China announces, sorry, we don't have anything else for you. Everything we produce of our heavies is going to our own internal demand stimulation initiatives, robotics, what have you. What do we do then? What do we do?
We have limited options. We either find a rapid solution, right? I mean, because stockpiling only works for so long. But that's kind of a policy decision. But from a geologic and supply chain point of view, that's what I'm fighting against. That's what we're really trying to get the state of research and the state of understanding of our policymakers to a point where we can hedge against that. I don't know how long it's going to take to get there, but I think that train's coming into the station at some point. At some point, they'll turn those inside. And you've already seen, I read the Wall Street Journal. I read some of these market reports as you already start seeing China's diverting more and more of their heavies into their own production. And that creates a problem. That creates a problem for us. And the answer is if we really want to produce heavies and we don't want to do it quickly, go back and look at the model for World War II. We produced metals very quickly in that scenario. However, part of the work that I did in the 90s was cleaning up some of those mines that we opened up and we ran hard in the previous two world wars. I don't think anybody really wants to go to that kind of crisis where the Defense Production Act puts soldiers and people into and produces stuff and we have to let the environment be less of a concern. I don't think that's something that we want to do. China's already sold their soul and their environment to get where they're at. We don't want to do the same.
Yeah.
I wish I had a magic answer for you. I still think we have time before that train runs us over, but we have to have an integrated strategic approach to how we get there. And that is probably, we look at the most vulnerable metals and we bring them to the finish line first, and we let other metals that aren't quite so vulnerable or that we can find other workarounds come to the solution point later. I don't think we can bring all 60 critical elements to the solution state at the same time.
Makes a lot of sense. Dustin?
Travis, listening to you talk, you're echoing a lot of the things that we've shared on our website and throughout the podcast. However, in your professional opinion, it's going to be an uphill climb, of course, to become independent on our own, to supply ourselves with lights and heavy rare earths. Is there hope? That's the question. Is there still light at the end of the tunnel, or have we simply just run out of time?
No, I am typically an eternal pessimist. I always say my glass isn't half empty, it's 3/4 empty. But in this case, I'm seeing the real innovation and looks a lot like Silicon Valley. Small, clever people are driving to a solution state very quickly, and they're not waiting. They're hoping that the market stability comes and there's ways to hedge against that risk. But you're seeing a lot of organizations really step up and do things that are incredibly innovative. Looking at, for instance, addressing the heavy problem. We're just going to have to accept that heavy rare earth production is not going to look like Mountain Pass. They're going to be smaller deposits. They're going to be smaller operations, but we don't need 22 million tons of rare earths, of heavies, right? So we can get away with that. And so the optic changes, but man, I sit around and listen to some of these startups and some of these new folks making entrees into the world. And I'm really, and especially when you start seeing investments start rolling in, that's really what the difference was, is that investment would only risk their money for a short period of time, and mining requires a longer viewpoint. But you're starting to see the investment side starting to link up with the production side. And I think that's great. I think so I've got a lot of hope on the mining side. Listen, there's something in our genetic makeup as human beings that we like digging metal out of rock. I don't know what it is, but some of the earliest things that we ever did, was what were to find a way to extract metals from rock, going back 10,000 plus years. So it's in our genome somewhere. The big gulf is going to be, you produce them, now what? We have got to build refineries. We have got to build separation plants. We have got to build manufacturing that can take them on. And we've got to do it because in the end, we are still a capitalist-driven organization. If I produce the metal and it's a really nifty metal from a nifty deposit and it costs 15% more than what China's willing to sell it to me for, right? These things, they're fungible. I don't see a wise corporation and the board of trustees sitting on the board sitting there saying, yeah, we'll go ahead and take a 15, 20, 50% cut to our profits just so we can buy internally. Even the flag is really important to a lot of companies, but it's not so important they're willing to lose money.
That's a very important. Dustin, I know we're getting close to the end. I think this is very important for Travis and the lab. You guys are doing incredible work. Since we started this venture, end of 2014, you came on our radar and we were already appreciative. Let's say, can you just do a high-level overview of services for the lab? And I think what's really important is innovation. There's a lot of investors out there. They come to rare earth exchanges. There's entrepreneurs. There's policy people in government. What are some ways that groups can engage with INL and help solve some of these problems?
There's a number of ways. So we do business with the private sector directly. Now there's something by law, we don't compete with the private sector. So if somebody can do it in the private sector, we're not allowed to compete there, nor should we. But in areas that require cutting edge technology development, imaging, separation development, we'll take an ore stream, we'll work out a flow sheet, we'll test that flow sheet for you, and we'll look and we'll refine it. So for a good example is work that we're doing for Perpetua. We're testing their antimony circuit, and that'll go live later this spring. And you'll be able to come and see it. It'll be open for people to take tours and visit. But that'll run about a ton per day for about 5 months. And that's essentially and that'll be the first of its kind pilot scale project where that's what we can do is we can work at those scales. We work at the bench scale as well, but how does what you're doing at a gram translate to what's going on at a full refinery or a full concentrator? So that's the delta that we're trying to provide. So we're really pleased about that. And we have a number of other organizations that are looking to do piloting projects here. We're looking to build out a new piloting facility out at our desert site at 45 miles west of where I'm at right now and bring this problem to a solution. Because like I said, a lot of clever research goes into figuring out the first gram. Then a lot of research is needed to figure out how to make that, to get the first ton. And we do that. But I also want to say that we are, I don't work for the Department of Energy, but I work at a Department of Energy laboratory. The investments that are made by the federal government through the Department of Energy and through the Department of War are crucial to the work that we do here. And so, like I say, through the metallic thing, we're going to be able to bring in some analytical equipment that just isn't available elsewhere. And we're going to be able to have that equipment work specifically on critical minerals and provide the kind of imaging and the kind of understanding pre and post and during processing that is required. So yeah, we're an open shop. We're growing. I'm growing my team all the time, looking for new, clever young people to come work here, and even some gray-haired folks that kind of come in and come to work for us. But we're not alone. National Laboratory is part of a national lab network. And each of those national labs have amazing capabilities, and some of them overlap a little bit with us, and some of them are different than what we do. And I think that's what Metallic has tried to do, is to take the capabilities of these labs, the member labs, the 9 labs that are part of it, and say, all right, your specialty is in this area. Here's the equipment needed to do that work at a higher resolution. And so INL particularly, we look at what's in our nearest neighborhood. We've got all these great reserves and resources next door in the states around us. Let's get them to market. So I've worked at INL for almost 35 years. I am happy to talk about how great a work we do, and we do wonderful work. But I also want to let the country know that the national lab system is for them as well, and the other national labs do fantastic work as well. If we can't do it, I will happily point the potential customer towards one of my partner labs and help them that way.
That's incredible service and a mission critical national security service. So we're going to keep writing articles about you all and supporting your efforts. Dustin.
Yeah, we'd like to have you come up and see what we're doing too. It's
yes.
Exciting.
That's on our to-do, is at some point we'd like to come up and bring a podcast up there and do it from Idaho National Lab.
Yeah, we'd love that.
That'd be awesome. And Travis, thank you so much for taking the time yet again to be on the show, share your knowledge, your perspective of this industry. Truly great conversation. And for those who are listening to this, if you liked it, please give us a thumbs up to wherever you are listening to the podcast. If you don't want to miss a future show, subscribe. Travis, thanks again, and we'll be in touch for sure.
It's absolutely my privilege, and I hope I didn't confuse too many people. This is a great field. We need more geologists. Send your sons and daughters to school and let them learn rocks.
100%.
Thanks, guys.
Thanks, everybody. I sure appreciate you. Bye-bye.
You got it.